We're going to talk about map algebra now. It is a way to put rasters together side by side. It's actually a good way to understand the way a lot of raster tools work. So rasters are arrays of numbers, you may recall, and if we can line them all up with extent and resolution, which this happens on the fly, um, we can use this map algebra to overlay these things. So see on the left here we have this example. We have a cell. 5 plus 3 is 8. So cell by cell, 7 plus 2 is 9. 2 plus 1 is 3. 6 plus 4 is 10. So we have a map algebra expression that adds two rasters together, and that operates cell by cell. It actually depends on what the operator is, but things like plus and minus and divide, they all work cell by cell. So, for example, say you've got a precip raster that's in inches and you want to have it in centimeters. Well, you use map algebra. You can take the name of the raster, multiply by 2.54, and you'll get a new raster that's in centimeters instead of inches. And then that new raster is output. Away we go. Another way we put these things together is raster queries. And raster queries, the idea is you can take a raster and cell by cell do some kind of Boolean operator. A value is less than something or greater than something or whatever. And so you can query a raster. And you may recall when we do a query on rows and we kind of light up some polygons, we can kind of do the same thing with cells. But you can do these expressions like a logical expression within map algebra, and what you get out of it is what we call a Boolean raster, where we have areas that are true, which is 1, or false, which is 0. And when we have a 1, 0 raster like this, we call it a Boolean raster. And what's kind of cool is if you have these 0, 1 rasters, you can use them together with more map algebra expression to compare multiple conditions. So for example, remember our good old friends and or? This at the top is a little Venn diagram on the left. Remember those things. I hope that's not too much of a trigger problem. But if you and them together, you get the cells that have these. Imagine these are two rasters that kind of overlay. We put them together. A and B gives us those values. And these are little truth table things where here's an input raster on the left and an input raster on the right. If we and these two rasters together, false and false is false, false and true is true, and true and false is false, and up in the upper right corner, true and true is true. So you might notice this is the same. This and is the same as doing a multiply. 1 times 0 is 0, for example. So and is kind of cool. So or is different than that. You take these two same input rasters and or them together. It's only false if both of them are false. So here's how all that works. Here's exclusive or, that really weird one where it's one or the other but not both. So cell by cell with these two rasters, it comes up this way. On these bottom two cells, either one or the other is true. See, true, exclusive or false, false, exclusive or true. These top overlays do that, basically give these both come out false. And then there's not, which you can use, which is A, not B. So that's the way this works out up here. This only happens if A is true and B is false. You get false. And not is only true when it's true here and false there. Okay? True, not true is false. So you can play around with these and see how they work. And or, just like before, are the ones we use the most. So here's kind of more detail on that. So how these relate to vector equivalence. Okay, raster overlay is often done cell by cell, and that can be done using that raster calculator is a very common way to do it. Now we've done overlays with vector data, but we can also do it in raster. And one big advantage of doing things in raster is it can be very fast. So if we want to try different things, we can try them very quickly. Another thing that's handy about it is that you don't deal with slivers. Everything cells. So things are a little easier things are less complicated because we don't need to worry about boundaries lining up. Everything is done cell by cell. And often a way to do this is we can do a raster version of the same analysis we did in vector by making a bunch of true or false rasters, 0 or 1 rasters. Then we either AND them all together or multiply them all together, we get the same thing. And this is how that works in the raster calculator. So in the raster calculator, we can you can use an AND operator, which is an ampersand, or we can use star to multiply them together. So all these inputs are 1, 0 rasters, and the output is going to be a 1, 0 raster. So here's what that looks like when we put the rasters together, is a Boolean overlay. So we come up with a bunch of conditions and we AND them together, and then here are the cells where both of these is true. If either of them is false, we get false. And note this is false, not no data. There's 0 that we get out there. So AND, remember, is the same as multiplying with 1, 0 grids. So away you go. We can also, instead of doing ANDing, we can do additive Boolean overlay. This can be really helpful when you have a range of conditions and you don't want to just a true or false output. You want ranges of things like good, better, best. Okay, and if you have here we have two rasters that are Boolean rasters, and if we add them together, we can the biggest value we get is 1 plus 1, which is 2, right? So you get a whole range of values. So this is called additive Boolean overlay. Okay, Boolean overlay does have some drawbacks. It makes it harder to get a gradation here. You have a couple levels here, but not that much. Here's a sample had where we have three different rasters we added together, so the maximum is 3, 1 plus 1 plus 1. But we do have some drawbacks to this. And conditions may be more conditional than true false. So the lodgepole example, 1500 may be suitable, 1501 is unsuitable. We might want to be a little bit advanced with this and reclassify this raster into 3 levels, where 0 to 1000 is unsuitable. Okay, 1000 to 1500 is somewhat suitable, 1500 meters is ideal. And we can do what's called weighted overlay, and that's kind of cool. In map algebra you can put those together. So remember, this all works cell by cell, and so you get a range of things. So here's an example of siting a landfill. So imagine we're trying to figure out a landfill. So we have a study area with a bunch of grid cells on it, and we set up a bunch of layers. Lower slopes might be better, okay? So we have a slope raster we might put into ranges. Low soil infiltration is important to save us from messing up the groundwater. Closer to roads is better, so that's good. And further from streams, which is the opposite, is better. We want to stay away from the streams. So we have 4 conditions, and then we can rank them all in a scale from 1 to 3. So this is how that looks in the suitability model. We take our inputs and we reclassify them into scores, okay? Where 3 is good, low slope, 1 is bad, high slope. We can build a landfill on a high slope, but it's expensive, so we really don't want to go there. So here are these ranges. Infiltration, remember, low infiltration is good, so we give that a high score. High infiltration is bad because we can contaminate the groundwater, so we give that a low score. Okay, distance to roads, they're the same way. Close to the roads is good because it's cheaper to take the garbage there. Further away from the roads, we'll have to build some roads, so that's less suitable because we don't want to go there. It'll be a lot less work. Distance to streams, now this one is different because near the stream is bad, so we give a really low score to near the streams. We make that 1, and if we're far away from the streams, that's good, so we give it a 3. So we put these scores all together, we classify our data, and we get these score rasters out that are ranges of scores, and then we can give them weights and we can add them all together. So here's how that calculation works. Here's that slope and infiltration and road distance, stream distance. Remember, these are scores from 1 to 3, and we can put them together and give them different weights. All these weights should add up to 1. So in the end, we'll get a map that goes from 1 to 3. Okay, in the output when we add all these together. So on here's our suitability map. You can see this kind of pulls suitability from all these different layers, where you can kind of see where the streams are. Those are really bad areas. Dark areas are good places to put a landfill, where all these things are met, where we're nearest the road, we're away from the streams, all that good stuff. So that's how that works. So that's the end of our thing on doing raster calculator and map algebra to do suitability analysis. And there's a nice little example you'll get to play with, and you'll see how handy this is. What's neat about this suitability analysis is if you decide these weights aren't right, you can just change the weights and do it again and rerun the thing. And you can do a couple different scenarios. If you decide that you have money, for example, to go ahead and cap the, put a layer of clay underneath your landfill, so you can basically don't have to worry about infiltration. You can take this infiltration weight and make it a little higher and lower another weight. As long as these weights add up to 1, you'll be good. So that's suitability analysis.